The definition of limit is of capital importance in calculus and its applications. Without it, concepts such as continuous functions, derivatives, or integrals would be practically impossible. In my view, to fully understand this definition, it is helpful to consider the simplest possible case, which in my opinion is the limit of a sequence of real numbers. So let an be a sequence of real numbers, and we want to give a definition to this. An goes to L when n goes to plus infinity. Intuitively, the idea is very simple. We say that an goes to L when n goes to plus infinity, with L here a finite value, if an gets arbitrarily close to the limit L, provided n is sufficiently large. The challenging part is to transform this informal idea into a precise definition. Indeed, here there are a couple of points that may contain some ambiguity because they are subjective. For example, what does it mean to be arbitrarily close to L? And what does it mean that the index n is sufficiently large? You see, terms like close, far, large, small are subjective. So we need a definition that everyone can agree on and that even, say, an alien could agree with. The solution to this puzzle is the following definition. So we said that the limit of the sequence an is value L finite if the following happens. So we start from the distance between an and the limit. We want that this distance be small. The distance between two numbers in the real line is given by the absolute value of the difference of these two numbers. So in this case, absolute value of an minus L. We want that this quantity be small, so let's say smaller than some epsilon that in our intuition for the moment is a small number. We will solve this later. Now, in general, this property won't be true for every element of the sequence, so that means for every index n. So we expect that this will be true provided n is sufficiently large, say n greater than some initial capital N. About this initial capital N, we may realize that it will depend on epsilon, because if you pretend to get closer to the limit, taking a smaller epsilon, you will have to wait a bit more, so to take a larger index. So in general, this n will be determined by epsilon, and it will depend on epsilon. Finally, let's talk about epsilon. Now, to ensure that regardless the value of epsilon considered small, we are still satisfied, the property we have written must be true for every positive epsilon. Well, now we have the formal definition of limit. To learn this definition, the best approach is to practice it with some example. Let's consider the limit here, when n goes to plus infinity, of n over n plus 1. We want to verify that this limit is equal to 1. Notice that this is very intuitive. If n is very large, the difference between numerator and denominator is 1 unit out of n. So for example, if n is 1 million, the denominator is 1,000,001, and the difference is 1 unit over 1 million. And when the numerator and the denominator are very similar, the fraction is very approximately close to 1. So this makes sense. Now, to verify that this is true, we need to verify this property. So let's write it. We have to verify that for every epsilon positive, we can find an initial index capital N such that the distance between the element of the sequence, which is here, n over n plus 1, minus the limit 1, is smaller than epsilon for every n greater or equal than capital N. Now, this is the property written, and the question is, what have we to do to verify this? Well, if we focus on this part of the property, we can see that this is an inequality where epsilon is fixed, is taken arbitrarily positive but fixed. And we have to say that this inequality is verified for every n larger than a certain capital N. So we have to determine this capital N. And how can we do that? So we take this as an inequality and we solve it. So we find all the possible solutions. And we try to see if among all possible solutions there are all naturals greater than some capital N. So first of all, let's solve the inequality. To solve the inequality, we may notice that since this fraction has numerator strictly less than the denominator and it is positive, this number is less than 1. So minus 1 is less than 0. So this is negative, and the absolute value will be the opposite. So this means that the inequality is equivalent to 1 minus n over n plus 1 less or equal than epsilon. Now this is a pretty simple inequality. We can solve with standard methods. So for example, we want to multiply by this factor. In this case, remind that n is natural, so n plus 1 is positive. So when we multiply both sides of this inequality, nothing changes. So n plus 1 minus n less or equal than epsilon times n plus 1. We can cancel these two n. So it remains epsilon times n plus 1 greater or equal than 1. Now to isolate n, we want to divide by epsilon. This can be done without problem because epsilon is positive. So we get that this is equivalent to, say, n plus 1 greater or equal than 1 over epsilon, or if we want, n greater or equal than 1 over epsilon minus 1. Notice that the existence of such n is ensured by the Archimedean property. Now, can we say that all n larger than some capital N are solutions of this, which is equivalent to this? Yes, because if this number is less than 0, negative, we can say that all natural will be greater than this because they are positive. So we could take as capital N just 0, and it would be true. If this number is positive, we could take as capital N the first natural after this number, which is the integer part of this number just plus 1. So the capital N would be integer part of 1 over epsilon minus 1 plus 1. In any case, you can see that we are able to find an initial n such that for all n greater or equal than that capital N, we have a solution of this inequality. So this property has been verified. Well, that's all. What can you do now? You can practice the definition, apply it to some simple cases like these ones. Doing this exercise is important because it helps you to understand the definition of limit and makes it easier to assimilate without having to memorize it, which is always a bad and dangerous practice with mathematical definitions. Then you could try to deepen your understanding by exploring some general property that is doing the same work as the examples, but in a more abstract way. For example, you could try to prove that if a sequence AN has a finite limit L, then the sequence of the squares, AN square, has limit L square. Of course, in this case, you have to argue without a specific sequence AN, but on a generic sequence, and the unique information you have is this one. Good luck.